let's say I have a bar. Okay. Let's say there is an end load. Let's say, give me some number, say 15 Newton. Okay. Now, apart from this, I also have force acting along the bar in the axial direction, but distributed over the length. Okay. Let me call this as some, let's say, B Newton per meter. Okay. B is this distributed force. Okay. And I seek to find out what would be the internal force created because of B and 15. Okay. How do I do that? Any suggestion? How would I do that? How would I find out the internal force?
Sir, at x distance, you can take a small element.
Correct. So what I can do is, let me make it. All right. So no problem. So I have, let's say this is positive. I also now have to introduce what's the difference between this and this? What is this and what is this? Quickly. What is this and what is this?
So first is sign convention.
For which one? This one is sign convention. First is for external forces and this is for internal forces. Fantastic. Right, Clifford. Right. So I put these two together because sometimes we may use this, sometimes we may use this. Okay. And this is sign convention, okay, which is necessary for internal forces. And this is for the external forces, or in other words, this is the fixed frame, fixed coord system. Okay. So given this, what can I do? I can probably cut a section like this, right? And when I cut a section like this, let's say this is x away from the support. So what am I doing? I'm basically assuming that this is the x and y. So for okay, y may not be necessary in this particular case, but x is what I'm fixing now. So I'm fixing with this fixed ball, right? So I'm now separated. Having separated, I should reveal an axial internal force. Let me call that as A. And this is at X. So I'll call it as A at X. So far, okay. All right. And I also have the internal force. This is, the external force here, which is B Newton per meter. I can remove this and insert a reaction force over here. Let's call this as A and this as B. So this is a reaction at A. Any questions so far? This is very simple, right? Remember, I'm using this being internal force, whether it is this or this, it is the same. How do I know? Cut a small section over here, and if you look at this, it will be like this. This is A of x, and this is A of x. Assume that this length that I've taken is very, very small, dx tending to 0. Okay. Ask me questions in case you have difficulty understanding this. So far, okay. So I can use this and carry on with finding out what this AX would be, right? What would be that AX? One way to do that is I'll take this side instead of this side, and this would be, let's say this length, total length is L, and this would be L minus X. Okay. Why am I doing this? Well, I don't have to find out this RA. That's why I'm doing this. If you wish to find out RA first and do it, then left hand side itself is okay. Okay, that is your choice. Whether you want to take the right hand side and do it, or left hand side and do it is your choice. Okay. What do I need to find out? I need to find out A of X. Okay, that's very simple. Sigma F along the X direction is equal to 0. I already have the convention that I'm using. Which one do you want to use? Let's say for this I'm using, then it is, okay. This is in the opposite direction, minus I of X. This is B acting over a length L minus X. So it will be positive B times L minus X, because remember this is force per unit length. So B times L minus X plus 15 is equal to 0, right? From which it is possible for me to find out A of X is equal to 15 plus B into L minus X. Very simple, correct? Any questions on this? Any questions? You've done this earlier, correct? Right? Now I'm going to make a little departure and try and find out something else. Okay. If you don't have any questions, I'll move on. Okay. Now, why did I say it is okay to consider this or this? What made me say that you can consider this or this? What is that condition that helped me say that I can use the left hand side or the right hand side? Determinant, what else? No, this 15 Newton that is acting at the end, right? So answer this question. What was the reason for saying, okay, you can either use left hand side one or the right hand side one? The unknown A. What condition helped me do it? What condition helped me do it? Equilibrium. That is, this is an equilibrium, this is an equilibrium, and supposing I cut this off somewhere here and then cut like this, will this be in equilibrium? Will this be in equilibrium? Will this be in equilibrium? The answer is yes. Every whatever cut I make here, every one of those free bodies would be in equilibrium. Correct? Right? So I make use of that and go ahead, write a little bit differently. I'm going to erase this. Okay. But before I erase it, what is this useful for? I can write this expression like this. I can also now say, okay, I can draw this to be something like this. Okay. So this is, I already know it is 15 newtons over here. It is linearly varying till it reaches here, where I had to put X to be 0 so that I get 15 plus BL, right? Newtons. Okay. And this is the positive notion. Why? Because this sign convention was used and I used that as the positive notion. So this is the positive value that I'm getting. And this is called the axial force diagram. Okay, we drew this earlier. I'm just reminding you about this. Okay. All right. Let me erase this. Okay. What did I do? I made a cut here and revealed this. Correct. What I'm going to do is, supposing, watch this carefully. Supposing it is some other point which is cut and that is equal to x plus delta x plus delta x. Let me retain this section. I take this section also. Okay. What will I get? I'll get a free body, which is this. I'm going to draw that free body. Watch this carefully because this is the crux of the whole thing that we will start to explore more. This is one force. Having cut this, it will reveal another internal force, right? And there is a body force over here, which is B. Okay. Any other thing that I missed over here? The answer is no, right? Now at X, when I cut this, I made it AX, fine. But if I move to X plus delta X and cut, this should be what?
X plus delta x.
Yeah, A at X plus delta X. Okay. Now this is an equilibrium, is a condition that I can apply, which means what? Sigma Fx is equal to 0. And this being positive, remember the notion that I've used here, this direction is consistent with positive. All right. This implies A of x plus delta x minus A of x plus B, and let's say this length is delta x, I'll get B times delta x is equal to 0. Okay. So now by now you understand why I'm doing this. Now I can divide throughout by delta x so that I'll get now A of x plus delta x minus A of x divided by delta x plus B is equal to 0. Limit as delta x tends to 0. I'm going to put it over here. Limit as delta x tends to 0 will give me dA by dx plus B equal to 0. Right? What's the difference between the earlier equation and this equation? This denotes equation for equilibrium of what? At any point. So any point of this rod is in equilibrium. And there is continuity maintained, right? There are two things that you have done so that there is a continuity of this internal force and not uniformity, but continuity. There is a continuity, or in other words, A should be differentiable. Okay. Now, this is not enough. This is not enough. This does not solve me the problem of finding out A of x. There's something that is missing. If I take a small piece over here, this is A at L, correct? At AL, and this is 15 Newton, right? B is very small, which means that A at L is equal to 15 is something that I should add over here as boundary condition in order to completely write equilibrium, stating that, conveying that every point of this body is in equilibrium. Okay, dA by dx plus B is equal to 0 with A of L is equal to 15. Now, having found out the axial force, is it possible for me to find out the stress in this rod? The stress in this rod? What's the difference between AX and the stress in this rod? What's the difference? Area, right? So if I have to say that this is the stress, then stress is equal to A by area. Let's say the area is A, small a. Then this is A, then I can find out sigma of x to be A of x by A. Fair enough, right? Simple. Any questions? I mean, this is simple, right? I found out the stress over. In this case, if I have to convert this to stress equation, what shall I do? Well, that's very simple. Shall I erase this one? This instead of area, I need to now convert to stress. How will I convert? I'll write A is equal to area times sigma and insert it over here. I'll get A times d sigma by dx plus B is equal to 0. Right? What is B here? With what? With A by L divided by A is equal to 15. Okay. So this is something that I can do. Correct? What is B? B is force per force per B is force per unit length, right? Okay. And this area is the area of cross section, right? Now, if I divide, so this is already force per unit length. If I divide by area, I get d by dx, d sigma by dx plus b by a is equal to 0. So far, okay, with whatever condition that I have here. Now, I already have unit length over here, and this is area. Length times area is length times area. I'll get it to be volume. And therefore, now I can write it to be d sigma. Okay, this is actually along the x direction plus d by dx plus I'm going to use a different notation over here. Let's say d bar is equal to 0, right? With whatever I can write over here, that is a times sigma L is equal to 15. And this is specific 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 completed force. Fantastic. Okay. We also call this as body force. So any body force that I have, I should multiply by volume in order to get the force. Okay. If you elect to call it as body force, you can also add density to this body force density. Okay. Questions so far? Is this clear? Right? So what did I do? I cut the bar, revealed the internal forces, and I could write an equation like this. I'm sorry, an expression like this. This equation essentially tells me that I can find out this value of A at any point by solving this equation, right? And then what we did was, well, if I have to calculate stress, then I can write it like this. What kind of stress is this? Sigma. What assumption did I make? When I drew something like this, and called it a sigma at x, what assumption did I make? Uniform distribution throughout the area, right? I'll give points to all the three of you, Karthik, Mohammed, and Harsha. Now, we call this as, we'll give some other name to this. Uniform cross section is fine, but by doing this, I have just made it an average stress. Is it not? I found out average stress over the cross section. And that average is, as you rightly pointed out, it is uniform through the area, right? This is a big assumption that I have made. What is the other assumption? Somebody said already that it is along the stress is along the axial direction.